To verify the solution, we want to refine the mesh to ensure the results are independent of the discretization. Back in the Workbench window, right-click on Model in the original module and select Duplicate. This creates a new duplicate module that we can name Refined Mesh. This module is linked to the original. This means that any changes to the original geometry or engineering data steps need to occur in the original module, and they will be propagated upwards. We can, however, make unique changes below that. So double-click on Model to open Mechanical. In Mechanical, start by clicking the Z-axis in the bottom right corner to fix the view. Next, in the tree, we can see that our axisymmetric 3D visualization is still active. We want to remove this to more easily compare the results. So right-click on Symmetry in the tree and select Delete. And click Yes. To reduce the discretization error, we want to create a finer mesh by reducing the element size. Start by selecting Mesh in the tree. In the Details pane, change element size to 0.05. And click Update in the top bar to create the new mesh. When this is complete, we can see that the discretization is much finer. With the new mesh, we can perform the solution process again by selecting Solution in the tree and clicking Solve in the top bar. With more nodes, the solver will generate more algebraic equations and find the displacement at more points. When the solution is complete, we can again investigate the stress contours and compare them to numerical results. This table shows results for the original mesh, the new refined mesh, and another mesh with even smaller elements. This shows that there is very minimal variation between the different meshes, meaning that our results are approximately independent of the discretization. In particular, the two most refined meshes with the smallest elements yield virtually identical results. Furthermore, we can compare hoop and axial stress results from the mesh with 0.05-inch element sizing to the theoretical results for both a thin and thick-walled pressure vessel. This shows that our finite element model agrees very closely with the analytical thick-walled model, with differences less than 1%. Additionally, we can see that both models vary significantly from the thin-walled model, with differences reaching almost 20%. This demonstrates the importance of understanding the assumptions of different engineering models. Finally, we can compare the radial stress results to the applied boundary conditions. This shows that, as expected from finite element theory, natural boundary conditions are only satisfied approximately. In comparison to the original mesh, however, we can see that the values have converged closer to the exact value. Back in Mechanical, make sure to save your project.